Good evening, Earth Science students. Tonight's lesson is pertaining to the solar system data chart on page 15 of your reference table. Please make sure you have that out. Please update your table of contents. Make sure whatever is in yellow font is in your notebook for your notes. And make sure the glossary terms are updated in the back of your book. All the terms are uploaded on Jupiter. It's under Unit 9, Topic Astronomy. All right, let's begin. Planets. Largest of non-stellar celestial objects that independently revolve around a star. Our planets include or consist of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Planets. Terrestrial planets. Alright, so the planets Mercury, Venus, Earth, and Mars that are Earth-like in being relatively close to the Sun, mostly solid, and having relatively small diameters and high densities. Alright, so going from left to right, we have Mercury, Venus, Earth, and Mars. One cool thing here is that based on size, Earth and Venus are sister planets based on their size. Now these notes are in white font. You don't have to write this down, but you should have an idea of what these planets are, at least one of the key features of each. All right, Mercury, one of the key features of Mercury is that it's not the hottest planet. All right, so the first point, not the hottest planet due to the lack of an atmosphere. Outgoing infrared radiation is not trapped because there's no greenhouse gases or no gases in the atmosphere. Many impact craters on its surface due to the lack of an atmosphere. So any meteors that come into Mercury's orbit will crash and collide with the surface of the planet because there's no gases to create friction to burn them up. One well-known basin is called the Caloris Basin. All right, it's the biggest impact craters on the planet Mercury. Next, Venus. Venus is the hottest planet in the solar system due to its dense atmosphere consisting of CO2. CO2 is a greenhouse gas, and these gases, right, there's a lot of it within the atmosphere of Venus, trapping in the outgoing infrared radiation. If you were to land on the surface of Venus, you would be incinerated pretty quickly. Another cool thing on page 15 is that it takes Venus longer to make one complete rotation than to make one complete revolution around the Sun. Mars, the red planet, due to the oxidation of iron-bearing minerals in its soil and rock formations. All right, it has the largest known volcano, known as Olympus Mons. Right, it's a shield volcano on the surface. Also has two polar ice caps, right? One up here in the north, one down here by the south. And there is water below the surface that's frozen, also known as permafrost. And that's below the surface of Mars. All right, so I skipped Earth because we've been going over Earth since September. So you should be well aware of the main things dealing with Earth. All right, let's continue. Jovian planets. The planets Jupiter, Saturn, Uranus, and Neptune that are far away from the Sun. They are largely gaseous and having large diameters, many moons, rings, and low densities. Now, all these planets, they have rings. Jupiter has a set of rings, but they're very faint. You can't see them that well. Right? The more pronounced ring system is on Saturn. There is a vertical ring system for Uranus, and also a very faint ring system for Neptune. So the outer planets do have rings. All four of them do, but the very more pronounced one is Jupiter. right? They have many moons. And you could actually see one moon right here, and its reflection is there on the surface, on the in the cloud formations of Jupiter. All right, so moons are bodies that orbit a planet or an asteroid as those objects that orbit the sun. All right, Jupiter. The largest planet in our solar system. Now, this planet, very unique. One thing that I have here is that it attracts any meteorites entering the solar system. It's called the boomerang effect. So anything coming in, and if it's under the influence of Jupiter's gravity, can actually take it, swing it down into the solar system, into the terrestrial planets, and bring it right back out. Again, if that falls under the influence of Jupiter. Right? So it's a good defense mechanism for Earth and the inner planets. Also, it's known for the massive planetary wind belts, right? There are numerous wind belts going across the surface of Jupiter, right? These wind belts are yellow in color, white in color, orange in color, almost like the planetary wind belts that we have on the Earth's surface. The last two things, is that the moon Io is volcanically active, and the moon Europa on the surface contains ice. All right, that's pretty cool for the moons for Jupiter. All right, and over here we have a very close up of the Great Red Spot, which is basically a massive hurricane storm or hurricane force winds. But these winds are much, much higher in terms of speed than on the Earth's hurricanes or tornadoes. Saturn, known for its massive ring structure, and its ring structure is composed of ice, and these crystals are very reflective, and that's why we can see the ring system for Saturn. All right, it's also similar to Jupiter, and it also has a series of planetary winds going across its surface. All right, Uranus, also known for its series of rings, right? So now its ring system is vertical, and its rotational axis is horizontal, and it spins in that direction. Last one is Neptune, known as the blue planet, and also for its great blue spot. All right, and there's a spot over here, the great blue spot, which is also similar to the great red spot on Jupiter's surface. Okay, apparently it's a massive storm, very high wind speeds going on at that one location. All right, and there's a few spots for Neptune. Space junk. Okay, so we have asteroid, we have meteors, meteoroid, meteorite, and a comet. Asteroid is a solid rocky and/or metallic body that independently orbits the sun. It's irregular shaped, mostly located between the orbits of Mars and Jupiter. All right, and within this asteroid belt, there are a few dwarf planets in there. Next, meteors. All right, meteors, path of light from a meteoroid burning as it passes through the Earth's atmosphere. This is also called a shooting star. A meteoroid, solid particles smaller than asteroids and comets that orbit the sun. A meteorite is a meteoroid that has landed on the Earth's surface. And the last thing is a comet, a low-density object composed of materials, ices, that easily vaporizes to form a tail. And it independently orbits the Sun in a highly eccentric orbit. And we mentioned during Kepler that high eccentricities would be very flat, oval-shaped orbits. Low eccentricity, low eccentric orbits, very rounded in shape. All right, so first thing, the asteroid belt. Asteroid belt is located between the orbit of Mars and Jupiter. So anything between those two diameters would be this belt of asteroids. And within this belt, we do have dwarf planets in there. We also have a Kuiper Belt. Kuiper Belt is on the outside portion of the solar system, right past the orbit of Neptune and Pluto. So you have two sets of belts, asteroid belt and the Kuiper Belt. All right, and also we have this Oort cloud of ice, methane, and some gases. Comets. All right, so we have this ice material which vaporizes in space, creating a tail. All right, so we have the formations of your tail, and the tail is always being in the opposite direction of the comet. And that's because of these solar winds from the sun. So the wind would push the tail outward in all directions from the sun. One famous comet that we have is Halley's Comet, which occurs every 76 years. It was also mentioned that all comets have highly eccentric orbits. So this orbit comes in and it goes back out, and it's very flat in comparison to the orbits of the planets, which are fairly rounded. Right, the only eccentric orbit that we have is Mercury at 0.206. Comets can be like 0.7, 0.8, 0.9. Very eccentric. All right, last few things is the evolution of the solar system. Okay, 1. Started as a gravitational contraction of gas dust cloud. 2. Most of the matter was pulled to the center to form the sun, right? Which we know that as the nebula and the protostar. The clumping of gas and dust occurred at the same time. 3. Larger and larger clumps formed, forming your planets and the moons, and this all occurred approximately 4.6 billions of years ago. Now that number is found in your reference table under page number 8, ESRT, under the geologic history. If you look at the Precambrian, it will say 4,600 millions of years ago was the beginning of the solar system and the sun, the formation of. Right, 4,600 millions of years ago is also equal to 4.6 billions of years ago. It's the same number. All right, again, that's found in your reference table. All right, so we have these formations, right? We have the contraction of gas and dust, right? We have the beginnings of a cloud formation like the protostar. We have nuclear fusion. We also have the clumping of materials on the outer portions. And eventually we had the beginnings of the solar system. And also, during this time, once the clumping became, or was going on, you had many impacts of these clumps just hitting each other and breaking apart. And sometimes these clumps under high pressure fuse together in a process called accretion. And during that process, it formed your planets, going from Mercury all the way out to Neptune. All right, so your densest materials were toward the center of the solar system, and your least dense materials were pushed out on the outer edges. That's why your outer planets are your gaseous planets, which are low densities, and your inner planets are high densities, mainly composed of solid materials. All right, we have two models. We have the geocentric model, which is the Earth-centered model. All right, geo means Earth, centric means center. So early in history, ancient Greeks, right, Roman Catholic Church, right, Ptolemy, all these ancient astronomers believed that the Earth was at the center of the universe. So in this picture, right, Earth is at the center, right? We have the moon revolving around the Earth. We have the sun revolving around the Earth. We have different planets revolving around the Earth. All right, but through the scientific revolution, through Kepler, Newton, Copernicus, Galileo, they came up with the heliocentric model, which is the sun-centered model. Helio represents the sun. Centric represents the center. So our sun is really at the center of our solar system, and all the planets orbit the sun, and our moons orbit planets. Let's do a few questions together. First question, which planet takes longer for one spin on its axis than for one orbit around the sun? You have Mercury, Venus, Earth, and Mars. All right, so we have those four planets, and we have to look at the revolution and rotation. All right, the question was, which planet takes longer for it to rotate than to complete one orbit around the sun? So Mercury, its rotation is less than the revolution. For Venus, its rotation is longer than the revolution. For Earth, rotation, right, is shorter than the revolution. And for Mars, its rotation is shorter than revolution. So the only planet for it to take longer to rotate once in one revolution is Venus. It takes 243 days to rotate once and 224.7 days to revolve around the sun. All right, so the correct answer for this one would be Venus. Another question, which graph best illustrates the relationship between the diameter of a planet versus the distance of the planet from the sun? We have our four choices here. Choice 1 is a direct graph. Choice 2 is an indirect graph. Choice 3 remains the same. And choice 4, it increases, decreases slightly, increases, and then decreases. All right, let's see which one's the best answer. All right, so look at mean distance from the sun. Right, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And we look at the diameter. So Mercury is 4,879, Venus 12,104, so it increases. Then it goes to Earth at 12,756. Still increases, but increases slightly. Then it goes to Mars at 6,794. It's going to decrease. Then it goes to Jupiter. It's going to increase dramatically to 142,984. Then it goes to Saturn. It's going to decrease 120,536. Then it goes to Uranus, 51,118. It's going to decrease. and then it's going to go to Neptune. It's going to decrease slightly to 49,528. So using that information, we know that we have some changes in diameter. So it can't be choice 1, it can't be choice 2, and it's not choice 3. All right, the answer is choice 4. It's going to increase slightly, right? It's going to decrease for Mars. It's going to increase for Jupiter. Right, it's going to increase for Jupiter, and then decrease for Saturn, Uranus, and Neptune. Next one, which planetary orbit model allows a scientist to predict the exact positions of the planets in the night sky for many years? Choice 1, the planet's orbits are circles in the geocentric model. Choice 2, the planet's orbits are ellipses in a geocentric model. Choice 3, the planet's orbits are circles in a heliocentric model. Choice 4, the planet's orbits are ellipses in a heliocentric model. All right, so currently, right, the old model is geocentric. The current model we use today is the heliocentric model. Based on our advances, we can eliminate choice number 1, which is geocentric. We can eliminate choice 2, which is geocentric. We're left with 3 and 4. The only thing now is, are the orbits circular or elliptical? So models, right? So we have the Earth as the center of one, and we have the sun located at the center of the other, right? So we know the current model we use is the heliocentric model, which is the sun. Next thing we need to do is look at under the eccentricity of the orbit, and we notice that every planet has an eccentricity. If the orbits all had 0 for eccentricity, that means every planet has a circular orbit. Round, that's it, bottom line. Since we have eccentricities, every planet travels in ellipses. All right, going back to the question, it's either going to be 3 or 4. Once again, it would be choice 3 if the orbits had eccentricities of 0, all the way up and down the board. But they don't. They have numbers. Based on that, the planets are ellipses, and the best answer would be choice 4. The planets' orbits are ellipses in a heliocentric model. Alright guys, so that would conclude this lesson. Come in tomorrow, we'll have 2 questions when you come into class. We'll have the intellectual engagement part, and we'll have a series of questions pertaining to page 15 of your reference table on planets and the data. Have a good night. See you tomorrow.